Chapter 1.10.5 Pod Topology Spread Constraints. Summary. Pod topology spread constraints ensure pods are distributed across different cluster domains like regions and nodes for enhanced availability and resource use. These constraints allow default settings for entire clusters or individual workloads, crucial for workloads with varying replicas to prevent single-node failures. Advanced features help reduce latency and network costs by efficient replica distribution across zones, ensuring balanced pods even with constraints. Pod topology spread constraints. Topology spread constraints help distribute pods across various parts of a cluster like regions or nodes, ensuring even distribution across failure domains. They support high availability and resource efficiency, and can be set for the entire cluster or specific workloads. Motivation. You have a cluster with up to 20 nodes and want an automatic scaling workload using 2 to 15 pods. It's crucial to avoid having 2 pods on the same node to prevent a single failure from taking your workload offline. Utilize advanced examples for high availability and better cluster usage. As you scale up, having 3 nodes with 5 pods highlights concerns beyond node failure, like increased latency and network costs due to different data centers. Address the performance issue by evenly scheduling replicas across zones to minimize latency and manage network expenses. This approach optimizes the performance within your infrastructure, ensuring efficient operation. Pod topology spread constraints allow for a declarative setup to achieve equal distribution of replicas across infrastructure zones, enhancing self-healing capabilities in case of issues in the cluster. Topology spread constraints field. This YAML code snippet sets up a topology spread constraint for a pod named example pod in the Kubernetes cluster. The constraint configuration includes parameters such as max skew, min domains, topology key, when unsatisfiable, label selector, match label keys, node affinity policy, and node taints policy. These parameters define how the pod should be spread across different failure domains within the cluster to achieve high availability and efficient resource utilization. This code snippet defines a topology spread constraint for pods in which the maximum skew between the number of pods in different topology domains is set to 1. The topology key used for spreading the pods is kubernetes.io/hostname, and in case the constraint is unsatisfiable, the pods are said to not be scheduled. Additionally, the pods must have a label selector that matches the label app, foo, and pod template hash. The code snippet defines a region as is-east1 and a zone within that region as is-east-1a. This configuration specifies the geographical location in a specific zone within that location where the workload can be spread across for high availability and efficient resource utilization in the cluster. The code shows a list of nodes in a cluster with their corresponding status, roles, age, version, and labels. Each node is labeled with a specific zone, either Zone A or Zone B, indicating their failure domain location within the cluster. Introduction to pod topology spread constraints. The Kubernetes Pod API introduces a mechanism known as spec topology spread constraints. This tool within Kubernetes helps the scheduler distribute incoming pods across a cluster to ensure balanced resource utilization. Users can access detailed information about this field by executing the command kubectl explain pod spec topology spread constraints. Also, it is explored in the *scheduling* section of the POD's API reference. Understanding spread constraint parameters. To guide Kubernetes scheduler on placing pods, various parameters such as max skew, min domains, and topology key are available. *max skew ensures a balanced distribution of pods by defining the maximum allowable difference, or skew, in the number of pods across various domains. Min domains optional marks the smallest number of qualifying domains a pod must satisfy. Topology key utilized as key node labels, it segregates nodes into topologies. Decision making with when unsatisfiable. The when unsatisfiable field instructs the scheduler on what to do if the distribution constraints can't be met. Do not schedule Default setting, ensuring pods aren't placed if constraints aren't met. Schedule anyway allows scheduling, prioritizing nodes that minimize skew. Elaborating label selector and match label keys. Label selector, are employed to identify relevant pods within a topology domain. Meanwhile, match label keys assists in selecting pod labels on which distribution calculations will be founded. Notably, a label cannot be duplicated across these selectors. Node affinity and taints policies. Two advanced fields, node affinity policy and node taints policy, are pivotal in defining how scheduler respects node affinities and taints. Node affinity policy outlines inclusion, honor, or exclusion, ignore, of nodes based on affinity requirements. Node taints policy determines if nodes with taints, fitting the POD's tolerations, should be considered. Comprehensive node labeling mechanisms. For effective use of spread constraints, nodes must be labeled accurately. Labels such as topology.kubernetes.io/zone or region are recommended over generic ones to prevent misinterpretation across different settings. Consistency. Set uniform pod topology constraints for all groups. Deployments usually handle this automatically. Mixing constraints can confuse Kubernetes. Consistent labeling of nodes in a group is crucial. This ensures everything works seamlessly without manual intervention. Clusters often auto-label nodes to help manage resources better. Verify your cluster's auto-label feature. Topology spread constraint examples. This code snippet defines a pod named myPod with a label foo bar and sets a topology spread constraint with a maximum skew of 1. Topology key is zone. When unsatisfiable is do not schedule and a label selector with a match label foo bar. The pod also contains a container named pause with an image registry.k8s.io/pause:3.1. This YAML code defines a pod named myPod with 2 topology spread constraints. The first constraint specifies a max skew of 1 for the zone key and the second constraint specifies a max skew of 1 for the node key. The pods will not be scheduled if the constraints are not satisfied. This code snippet defines a pod called myPod with a label of foo bar and sets a topology spread constraint with a max skew of 1. Topology key of zone. When unsatisfiable set to do not schedule and label selector matching foo bar. It also includes node affinity specifying that the pod should not be scheduled on nodes in zone C. Example. 1 topology spread constraint. In a 4-node cluster with zones A and B, where 3 pods are spread across zones, you apply a topology spread constraint. This ensures new pods spread evenly across zones labeled Zone A or Zone B. Nodes without zone labels are skipped. Using when unsatisfiable. Do not schedule. If a pod cannot be evenly placed, it remains pending. The constraint is unsatisfied if the pod causes a skew over max skew, e.g., skew can't exceed 1. New pods placed in Zone B lead to adjustment of skew within nodes, keeping it compliant with the policy. Adjustments can be made to max skew or topology key for desired distributions. Tweaking pod specifications. Modify max skew to allow more leniency in newly placed pod skew. Change topology key to node for even pod distribution across individual nodes, not zones. Utilize when unsatisfiable. Schedule anyway to bypass strict constraint adherence, ensuring pods are placed albeit less optimally. Example. Multiple topology spread constraints. Extends earlier examples by controlling pod spread both by node and zone. An incoming pod fulfilling all constraints must be placed specifically onto node 4. Scheduler only selects node placements satisfying all constraints. If none exists, pod remains pending. Conflicting topology spread constraints. Applying the same constraints in a 3-node, 2-zone cluster might cause incompatibilities. Conflict arises when a POD's allowed placement options, for each constraint, don't overlap. Potential resolutions include adjusting max skew, changing unsatisfiable strategies, or manual pod deletion in special cases. Interaction with node affinity and selectors. Scheduler skips nodes that don't fit affinity or selector criteria when calculating skew. Node affinity or selectors thus narrow down eligible nodes for new pods, potentially impacting spread dynamics. Example. Constraints with node affinity. 5-node cluster across zones AC has an exclusion for zone C manifest formulated to ensure MyPod, is placed in permissible zones, affirming the impact of node affinity. Kubernetes respects these constraints in node placement, especially when specific zones, nodes need exclusion. General adjustments and strategies. Modifying constraints caters to different scheduling requirements. Deletion of existing pods may be needed for progressing without cluster disruptions. Scheduled pods might remain pending if constraints are too restrictive or contradictory, necessitating periodic adjustments. Implicit conventions. Implicit rules guide how pods are matched within a namespace and scheduled. Only pods under the same namespace can be candidates for scheduling. Nodes must have all necessary topology keys for pod scheduling. If any keys are missing, nodes are skipped during scheduling, affecting how pods are counted towards balance calculations. When a node lacks labeling like zone, it doesn't count towards the pod placement. As seen in node 1's case, missing labels mean pods won't influence balance calculations and the node will be ignored for scheduling. Nodes with mismatched or mistyped labels are bypassed, as noted with node 5. If the incoming POD's labels don't match required criteria, there can be unexpected placements, requiring label consistency for proper pod distribution. Cluster-level default constraints. This code snippet defines a cluster-level default constraint for the default scheduler plugin named Pod Topology Spread, setting max skew to 1, topology key to topology.kubernetes.io/zone, and when unsatisfiable to schedule anyway. These constraints will be applied as default constraints for all pods in the cluster when no specific constraints are defined at the workload level. These default constraints set a maximum skew of 3 for the nodes based on the hostname topology key, and a maximum skew of 5 for the nodes based on the zone topology key. If the constraints cannot be satisfied, the scheduler will prioritize scheduling the pods anyway. This code defines a Kubernetes scheduler configuration for the default scheduler, specifying the plugin configuration for Pod Topology Spread. It includes an empty array for default constraints and specifies that the defaulting type is a list. Default topology spread constraints for a cluster apply when a pod lacks its own constraints. They are relevant for pods within a service, replica set, stateful set, or replication controller. These constraints are set in the Pod Topology Spread plugin's scheduling profile, using an API where label selector is empty. Selectors derive from the POD's associated service or sets. For Kubernetes version 1.24, the kube scheduler uses built-in default constraints if none are configured, disabling the legacy selector spread plugin by default. Note: the pod topology spread plugin requires topology keys. This differs from the legacy plugin. Absence might affect constraint behavior unless customized. If nodes lack kubernetes.io/hostname or topology.kubernetes.io/zone labels, customize constraints. Defaults can be bypassed by setting defaulting type to list in the plugin configuration. Comparison with pod affinity and pod anti-affinity. Inter-pod affinity and anti-affinity in Kubernetes dictate how pods are scheduled, by either grouping or dispersing them. Pod affinity attracts pods to pack them into specific domains, while pod anti-affinity repels them. These settings influence the number of pods in a domain. Topology spread constraints offer detailed distribution of pods for high availability or cost efficiency, aiding in smooth updates and scalability. Known limitations. Removing pods can disrupt constraints, causing an array of issues such as imbalanced pod distribution. Tools like Descheduler are useful for rebalancing. Tainted nodes limit which pods are honored. Refer to issue 80921 for more info. Schedulers lack knowledge of cluster topology zones. Zones are decided by existing nodes, which can complicate auto-scaling when a node group scales to 0, as topology domains aren't factored in until nodes exist. Cluster autoscaling challenges occur if node pools go to 0 and topology spreads aren't counted until new nodes are available. This affects scale-up expectations. Utilize a cluster autoscaling tool that understands both pod topology spread constraints and topology domains for smoother scaling.